Welcome to a video on the Wien-bridge oscillator. In this video we will be looking at the derivation of a Wien-bridge oscillator's design equations using Barkhuizen's criteria. Then I will allow you to do a design on your own, and then we will look at some simulations and then at how to improve a circuit using automatic gain control. But the design of a automatic gain control circuit is a different video on its own. Okay, so let's have a look at the Wien-bridge oscillator. So the Wien-bridge oscillator is an op-amp circuit or a differential amplifier of a sort. And if you look at the top here, we have negative feedback taking Vp as our input voltage. This is just a non-inverting amplifier. Okay, so that is our gain of our amplifier, the A in Barkhuizen's criteria. Looking down here, we have voltage division happening to get to Vf. So we can define this as a series impedance and as a parallel impedance. Okay, and I'm going to use Laplace, which is just S takes the place of j omega plus sigma, where sigma is 0, just to make these equations a little bit less complicated. So for the series impedance, we have Rs plus 1 over Cs, and for the parallel, we have Rp parallel to 1 over C parallel S, which you can simplify. And typically, you will choose the resistors and the capacitors to have the same values. So all the caps will be replaced with C, and all the resistors will be replaced with R. Okay, so plugging ZP and ZS in here, we are left with this monstrosity over here. Okay, so to simplify this, we can see that R over RCS plus 1 is common top and bottom, and typically we want just one left at the top of the equation, or something that has no imaginary components in it. So we multiply with 1 over 1, and it simplifies down to 3 plus RCS plus 1 over RCS. Replace S with j omega, so we go from Laplace to our frequency here. And lastly, we multiply with our gain. So AB for Barkhuizen's criteria should be 1 with a phase shift of 0. Okay, so our gain has no imaginary terms in it. This 3 has no imaginary terms in it. The only place where we have imaginary terms is j omega RC minus j over omega RC. Okay, so this is responsible for our phase shift. Okay, so to get rid of this, we'll be at the resonant frequency, omega 0. Okay, so this is where this part will disappear, and from this part of the equation is where we get our resonant frequency from. Okay, so j omega RC minus j over omega 0 RC should be equal to 0. And from that, our omega 0 is 1 over RC, or if you're dealing in hertz, 1 over 2 pi RC. Okay, then we take this omega 0 and plug it back into the original equation, and we are left with 1 plus R2 over R1 over 3, and this should be equal to our loop gain of 1. Okay, so the gain of our amplifier, so the negative feedback part, we should have a gain of 3. This will place us on the marginally stable line. Okay, so the ratio for resistor 2 over resistor 1 should be greater than 2 for oscillations to start. So basically when we push our system into the unstable region. Okay, so that is when oscillations will start if you choose your ratio of your resistors to be a bit larger than 2. Right. So, I want you to pause the video and quickly design oscillator to oscillate at 10 kilohertz and use 10 kilo ohms for your lowest resistor. Okay, then I want you to calculate all the required components, simulate the problem, and make some conclusions after the simulation. Right, so the solution is if the lowest resistor should be 10 kilo ohms, let's choose our resistor in the parallel and series networks to be 10 kilo ohms, so RS and RP should be 10K, and we can find that our capacitor should be 1.6 nanofarads. Okay, real world design, you will typically choose the capacitor first because there is less capacitor values available than resistor values, and for resistors there is E12, E24, E48. There is a lot of resistor values available if you need to fine tune an oscillator. Okay, so that is our first part. Is we have our RC, and R2 over R1 should be greater than 2, meaning R1 is the smallest resistor. Choose R1 as 10K to have a ratio a little bit larger than 2, we can choose R2 to be a 22 kilo ohm resistor. So let's start up our simulation, and during the simulation I will start with making conclusions. Then I'll get back to the last part of the presentation. Right, so I built our oscillator and I used a perfect op amp, so this poses some issues. So in the transient, ensure that you tick the start up or start external DC supplies from 0 volts down here. And with this simulation, initially I had some issues, so this top supply I just made it a pulse to cause some instability in our system so that it will actually start oscillating and not just provide a stable output, because there is no noise in a simulation. Okay, so any other videos that I do this, I'm not going to repeat that I pulse the input. You're just going to see it happen. So yeah, let's run the simulation and see what we get. So the pulse input happens a long time ago, so we can't see that. But if you click here, we see that we have a waveform that's being generated, but it is clipping at the limits of our rails. So let's make that 12 minus 12. Okay, so this amplifier is providing oscillations, but it is distorting. So we need to limit the gain of this amplifier if we want perfect sinusoidals. So this is part one of the conclusions that you should be making when looking at the simulation. Okay, so we need some form to limit this from happening. Second off, in any of these oscillators, we need to be able to define the distortion as a percentage what's happening here. And for that, we need to look at the frequency domain of a signal, because all frequencies can be expressed what's in this. So our fundamental frequency is a 10 kilohertz, but you will see that there is some extra harmonics added, which makes our output look strange. Okay, so the distortion, we need to be able to express it as a percentage. So there will be a video on total harmonic distortion and how to calculate it. Okay, but in short, we should have a peak and a minimum of these extra peaks for a sinusoidal. For triangular and square wave, you will see more of these peaks that actually makes up the output. Okay, so this you can see is already looking more like a square wave. Yes, you can see the curves of it making it the sinusoid, but it looks more like a square wave. Okay, so video on total harmonic distortion on how to express the amount of distortion happening in our circuit. And if you want the FFT to look nice, you should have more data to work from. Okay, the FFT will not auto refresh. So let's click this window and say FFT. And okay, and now we can see that our frequency is a bit off from 10 kilohertz and that there is a lot of harmonics playing a role in here. Some of this is noise, especially here at the bottom, so you can ignore it, and stuff that is smaller than minus 40 dBs is typically a second decimal for this problem and is not having such a large influence. Okay, there is quite a lot of them, so it can amount to a lot. And remember that this is expressed in dBs, but if you convert it back to volts, this is the RMS voltages of our signal. Okay, so we need a way to express our distortion, and we need a way to limit our output signal. Okay, so I'm going to jump over to a simulation where I added the automatic gain control and have a look at the FFT there and the output signal. So here is our circuit with limiting. So basically what happens is the moment that the output wave becomes too large, one of the diodes on positive or negative cycle will start to conduct and your gain will be brought down. So basically from an unstable system, bring it back to being a stable system. And with these resistors right here, you can also select the amplitude that you want out. Okay, so for this one, the chosen amplitude was 5 volts. And you can see that this looks much better as a sinusoid. There is some distortion left here on the edges, you can see, but this is due to the non-linearity of our diodes. Okay, so let me quickly make this simulation a tad longer so that we have better data for our fast Fourier transform. And if we do the FFT, you can see that there is considerably less harmonics here than in the circuit without the limiting. Okay, so let's jump back to our conclusions and what needs to be done in follow-up videos. So what we've seen is that we need some way to control the gain in our system, so some non-linear automatic gain control, so that we can choose our output signal size, and having automatic gain control will limit the distortion that we have. Okay, basic circuit with automatic gain control or a limiter. We will discuss that in a follow-up video. And then a comparison of the two signals. So our signal with gain control is looking much better than our signal without the gain control. And we need to do total harmonic distortion calculation so that we can properly compare the two signals with one another. Right, so that will be in the two next videos. Thank you for watching.